So my today's talk will be on research methodologies in hard sciences. And I've prepared a content. From this content, I will touch base on what we do at INANOS and then talk about research methodologies. From there, take you through the clarifications, research design and methodologies. Then another part of the talk today will cover the research plan, covering the objectives, reflecting to the objectives, the instrumentations that are used to characterize the materials, the budget, and the research outcome. Lastly, we will talk about the data management. So as Mr. Machila introduced to me, I am from the Institute for Nanotechnology and Water Sustainability, and we have two focus areas. We have water sustainability and nanotechnology. And I belong to the nanotechnology focus area under the applied electrochemistry. So the applied electrochemistry deals with the preparation of various materials, characterization and applications in sensors and electrocatalysis, energy materials, and capacitive deionization. I'm not going to go into details here. The type of materials that we use are nanocomposites, quantum dots, thiocyanide, and others. And once we have produced those materials, we apply them in detecting heavy metals, pharmaceutical contaminants, or biomarkers. So because I've touched base on the other theme, we have a theme on energy storage, whereby we are converting or producing fuel cells or batteries or energy storage materials. Now coming to what we're here for today. So in order for us to fully understand the methodologies in hard sciences, we need to be able to clarify the aims and the objectives of the work. For example, the research aim in this case will be the development of an electrochemical sensor based on nickel selenide quantum dot for nevarapine detection in water. Now, by looking at this aim, we are able to develop or break down our objectives based on what we are saying we are going to be producing. So since we are saying we are developing a sensor system that is based on a material based for detecting an analyte in water. So in this case, the objectives will cover the preparation of this nickel selenide quantum dot. So in this case, when we synthesize various materials, particularly quantum dots, we use various methodologies. So in this case, we could use sol gel, hydrothermal, electrode deposition, microwave assisted. So it depends on which method would work for your system. In other cases, we prepare these materials using a sol gel and microwave and compare which one is suitable for our material. So after the synthesis of these materials, so it's very important that we understand their signatures. We understand whether we have produced the sizes that we are looking for. So in this case, we characterize these materials using various, techniques. After the characterization, we have to actually optimize. What do we do when we optimize? We have to ensure that the parameters that we are using are correct, are for our electrochemical sensor system. After the optimization, we then test, that means we introduce our nevarapine in our sensor system. And of course, do some validation studies. Now, as I've mentioned in the previous slide, that we use various methods of synthesizing materials. Now, when we talk about various methods, the question will be, if you're preparing your topic, the question will be, how is this material that I'm producing novel? Is it new? Is there a way that I could come up with a method that would be novel? Or is there a way of modifying the existing method so that it complies to what you are trying to produce? So I've made an example here saying this is a procedure 1 whereby we are synthesizing a quantum dot using a colloidal synthesis. But if you're reading this correctly, you will see that yes, we have adopted a method from the previous work, but then because we want this work to have our signature, so we modify the procedure to fit our standard. And for this method, we were using an aqueous solution, which means we were using water as a solvent. Now, in another way, we could use the same, prepare the same material, but using organometallics or using dendrimers or any other material. So in this way, once we have produced these different procedures, of course, the results that we are producing will be different from one another, depending on what we were combining in procedure 1 and what we're combining for procedure 2. Now, this is just an example so that we can all visualize when we synthesize these materials. So we are saying we're producing materials for electrochemistry. So for electrochemistry, we normally use an electrode, and we modify these electrodes using the prepared material. But before doing so, we have to characterize using various techniques. So it is very important that you note, or we note, the type of technologies that will give us the information we are looking for. For example, if we are looking for the particle size, we will have to use HRTEM, which is the high resolution transmission electron microscopy. And we use a small angle X-ray scattering. Those two will give us information about the particle size and the shape. So before going to the lab or doing your experiments, you have to identify the technologies to be used for the work. Then after this characterization, of course, you can continue with the application of the study. As I've mentioned now that, of course, we use a small angle X-ray scattering. So from the small angle X-ray scattering, we are able to identify various shapes and sizes depending on the procedures that we use. So in this case, if we have or we produce a material and use a surfactant or a stabilizing agent, we would be able to get a core shell. Normally for functionalized materials, we have our core, which is a metal, and the shell would be, the stabilizing agent of choice we've used. And of course, depending on the metals that we're using, if we're using polymers, if we're using graphene oxides, we'll get structures like long rods or flat disc or hollow sphere, depending on what we are producing. But then, of course, when we're talking about the dumbbell, it means that we are combining two materials. In this case, we are preparing a nano composite. A nano composite means you are bringing together two materials to produce one. Hence, when you're looking at this graph, you'll see that if you're producing two materials, you will have two peaks, meaning you have a peak for one material and a peak for another material. And of course, though we have these two peaks, we will have some interactions of the materials that are combined together. Now, more information about the core shell structures and nanocomposites. I've indicated that a shell is something that is an outside from our core, which is the metal. In this case, our metal is the nickel and selenium. So in this case, once we introduce a shell, we will have a shell that is negatively charged. So we can easily say we have produced a core shell. But then for the nanocomposite, we are bringing these materials together. And then, of course, we'll have signatures of the two materials. Now, I think I've indicated in the first few slides that these materials can be, prepared using dendrimers, short-chained capping agents, or long-chained capping agents. When long-chained stabilizing agents are used, we normally look at the functional groups. The functional groups are the groups that are likely to bind with other functionalities. So if we are looking at this structure on the left-hand side, we can see that this is just a dendrimer within amino groups. But then once we introduce, some functionalities, we are able to change the structure of the prepared dendrimer. Now, those functionalized dendrimer can be used as a stabilizing agent for any material of choice. We are still linking all this with the title saying developing a sensor or developing a system for detecting or removal of, contaminants in water. So these are the steps that we follow. In this case, we synthesize, characterize, and then do the application. But for us to be able to go into deeper details about the application, we need to do a thorough work on the characterization to prove that the material we've produced is indeed a quantum dot. But then there is a nice thing that we normally do in hard sciences. In hard sciences, we use various techniques that would complement one another. So in this case, we are looking at the small angle X-ray scattering. Yes, of course, we are looking at the structure of, the prepared material. But now, how do we compare, or how do we now complement what we have in this graph with what we have on the right-hand side? Because these techniques are giving us the same information. But of course, this technique is focusing on the internal structure using a copper grid. Whereas this instrument, we're using it in solution or in powder form. So for this machine, we usually measure a small spot because those electrons that are coming from the HRTM will focus on one spot, and we are able to get the information about the shapes of what we have produced. And in this case, we understand that we have produced the core shell because we have said previously that the shells are coming at a negative region, whereas our core would appear in the positive region. And how do we now complement this to this? We look at the sizes of the particles that are appearing, and we are looking at the scale view on the right-hand side. Another important point is that for these materials, we can complement or compare the prepared materials with the commercial material to ensure that whatever we have synthesized is behaving much better than the commercial. The reason why I'm saying it's behaving much better is because the commercial one has some impurities, because there are so many mixtures that would be, be in that bottle. But then when you synthesize the material, we normally wash these materials to remove certain impurities. Hence, we are seeing the shape of the synthesized material, which is slightly enhanced in this region. Now, coming to the research design, I have listed the things that we touch base on today. So we have touch based on the preparation of the materials. We have also touched based on the characterization. So we are linking these with our objectives. So whatever we do in the lab or whatever we try to prepare, we link it to the objectives of the work. So the objectives must align with the experiments that we produce, also with the characterization that we use. So in this case, since we have done a certain part of the work, 2 objectives, so this is the third activity, which is now the fabrication or the development of an electrochemical sensor, which we talked about as the title of or research aim. So when it comes to the fabrication or the development, we usually look at different electrodes, or we look at different methods. I'll put it in that way. We look at different methods, the methods that would make it easier or would give us a better performance as compared to the other methods. And for us, we know that there are various methods that we could use. We have different electrodes that we can use. In this case, we have a classic carbon electrode, screen printed, FTO, and others. The selection of an electrode has to do with what we are trying to achieve. If we are trying to do a detection, we could use a classic carbon electrode. But if we are trying to do a detection and removal, we have to use an electrode that has a surface area or larger surface area. In this case, we could cover the whole part of this electrode because this one would do double work, which is the sensing and the removal of these contaminants in water. So planning is key when it comes to hard sciences, so that everything is linking to the objectives of the work. Now, the reasons why we normally look at materials is because of their, the properties. So you have to ask yourself about that. Why are we, selecting this type of work? What are we trying to improve by selecting this type of material, if it is a material? And can we use various stabilizing agents to improve on the functionalities? What can we do, to improve on the performance? What can we do to make this work to be my own? So there are various questions that we ask before, conducting the study in the lab, particularly the application part. Now, to make it easier, so I've indicated or listed the methods that we use for our fabrication. So in this case, let's say we selected an electrode, a classic carbon electrode or a gold electrode, and we modify or we attach a material that has, a certain affinity onto this electrode surface. So there are various reasons for doing so, because most of the time when we introduce our own materials, the produced or synthesized materials, they like to fall off from the surface of the electrode. So hence we introduce a material that would attach these materials on the electrode surface. And of course, once we attach these materials, we are able to do our detection, meaning that we are including various concentrations of the analyte. But remember, before doing all this, research design, we have to go back to the last objective, which was the optimization. After the optimization, we have to do the testing. After the testing, we do the validation of the work. So in this case, we have done a lot of work in terms of the optimization. We have optimized the pH because, we are going to be applying this sensor system in water bodies. And it's very important to know which pH is suitable for our system. This is our system. Yes, there are already reported studies about, sensors, but not specifically for this type of material we're using. And the reasons why we are optimizing this work is because we are trying to make it our own. So in this case, we used, various pHs, and we were able to see that the pH 7 was giving us a better performance in terms of the current, looking at the y-axis, and we selected the pH 7 to continue with the work. And on the right hand side, we were looking at the potential. We could see that from the potential, the pH 7 was still the best. So it is very important for hard scientists to optimize before going into the, to further studies. That will really, really assist in terms of producing high quality work for either master's or doctoral students. Now, another important information is that we are still on optimization, because optimization takes time. But as long as you understand your material and understand your sensor system, if it is a sensor. So in this case, we also optimize in terms of the electrolyte, meaning a solution that we use for, for our sensor. So we use various electrolytes to check which one is suitable for the work. So looking at these electrolytes, we could say the nitric acid, you see the blue is giving us a better performance. Also, we have two others, the HCl and sulfuric acid are giving us better performance than the buffer solution and sodium hydroxide. So we also continue by doing a lot of work in terms of electrode deposition. You remember that I've mentioned that we could create our own method depending on what we're trying to produce. So in this case, we have tried to look at the electrode deposition of the materials on the electrode surface, and we could see that at -0.2, this electrode deposition is working the best as compared to the other potential ranges. And in terms of the time, because we have to monitor the potential and also monitor the time in terms of seconds, and we selected 60 seconds because it was giving us the highest signature. Now, after the optimization using all these details, so it's very important that, because if we are producing a sensor system, we have to optimize in terms of the scans. How many scans are we going to use? Are we going to use a slow scan, or are we going to use a fast scan? And remember, these methods are different for chemists, for physicists, and for engineers. But when it comes to the optimization, each theme will be optimizing the materials, optimizing the methods in a certain way. So in this case, we are optimizing the scan rate, and we've selected a suitable scan rate which was appearing at a lower potential, which is a scan rate of 30. So after that optimization, we then focused on our application now, because our title was focused on the development of a sensor for nevarapine detection. So now we have started the work by doing our detection using different concentrations. But before doing this, it's very important that students go to literature and check what is the concentration of these contaminants in water. Once you have come up with that information, it's much easier to, prepare a stock solution for your material or for your analyte, and also a working solution for that particular analyte. In that way, we are trying to produce a linear range. For those who are doing analytical chemistry, they would understand, because we are trying to get information about a linear range, trying to get information about the limit of detection, and information about the sensitivity, because sensitivity is very important when you are developing a methodology. Also, efficiency, is very important. So now, looking at what we have produced here, we were able to draw a curve indicating all these concentrations that we have included, when we're doing the detection. Now, because we are saying we are looking for a linear range, when we are talking about a linear range, we are talking about a certain part that is linear. That means the linear range would appear from this region. This part is linear. Whatever that is on the straight line here, it means that the sensor system or the method that we're developing has reached its saturation. So it's very important that you go to literature, get information before doing your application, because sometimes you could use this concentration from this region to here, and you are not getting anything. If you are unable to get anything from those concentrations, it means that you have already started from an area that has reached a saturation. So it's very important that we go to very low concentrations to be able to get that information. Now, from there, we're able to draw our linear curve. For the information we get from the linear curve is definitely the linear range. And we can see that the linear range is wider, which is very good, because this method is going to be used in water, since our topic or our title is saying the detection of this particular analyte in water. So once we have this proof of principle, we then use the proof of principle in testing the water bodies. But before then, we know that in water, for example, there are so many contaminants that are there. And the question that we should be asking, if you are developing this type of research based on the objectives, because everything is linking to the objectives of the work, to the aim, what is the aim of the work and the objectives of the work. So we have done a lot of work on the optimization as well. But then now, how do we ensure that this method or methodology is only for nevarapine, for example? Because if I'm taking my method and employing it in water bodies, will it only detect the nevarapine that is there, or it will also detect other contaminants that are there? So that should be the question asked before continuing with the work, so that we get some evidence that indeed this work is only focused on the nevarapine sensor. So we have done a lot of work on the interference studies. In this case, we've used different groups from different, pharmaceutical contaminants. We've used from a different ARV drug. We have used endocrine disrupting compound and a painkiller. And by just looking at this graph, we could say that these drugs that we've introduced in our sensor system did not have that much effect. So it means that our sensor is selective, it's only for the nevarapine, because we are not getting much information about these contaminants that we introduce in our sensor system. So this proves that whatever we have produced, the method we have produced, is only for nevarapine, because our title or our aim was for nevarapine. And once we have reached that stage that, oh, okay, this is what we are seeing, because we have selected different groups, we then use our linear range from our proof of principle. Then we are able to do at least 3 samples of water, to be able to say, okay, this is our real sample. We've tested Nevada pin sensor in water because that was what we wanted to achieve. And another question we should always ask is that, how important is this work? Just before even starting, how important is this work? What would be the outcomes of the work? What would be the budget? Do we have the techniques that would give me this type of information I'm looking for? Do we have these chemicals? How much are these chemicals? So before going to the lab, so that you fully understand, the methodology and the procedures to follow. Now, giving just one other example about, complementing the work, because I've mentioned it earlier on that it's very important that you take one instrument and complement it with one another. And in this case, we've done a lot of work on the, scattering curve, and then getting information from the scattering curve and linking it to the particle size, particle shape, and also with the crystallinity of the materials. And of course, we look at the lattice fringes, we look at the globular structures or spherical structures using, various morphological properties. And of course, I have mentioned earlier on, I think when I was starting, about different stabilizing agent, that, we could use the same metal. For example, here, this copper selenide. But then from this copper selenide, the capping agent that I used are very much different. But then if you are looking at this, you can see that these different stabilizing agents are giving us different informations, and they are giving us different particle sizes. If you are looking on the right hand side, we are seeing that the particle sizes are different because of what we have used as a stabilizing agent. And even on the internal structures, we are getting different information. And of course, our diameters are different because we are using different materials. Now, another slightly different example, let us say now we are combining that electrochemistry with photo. We are combining 2 techniques. How do we go about that if we are combining 2 methods? Remember, for electrochemical sensor, we were using 1 method. But then now we have integrated or combined, having 2 methodologies together. How do we then go about that? So it's very important to fully understand the photo part and to fully understand the electro part, because they go hand in hand, So these are my references of the work, and yeah, thank you so much.